Hello friends, welcome to engineering tutorial. So we will continue our discussion with network theory. We were covering network theorems, and so far in network theorems we have discussed about superposition theorem. We discussed some questions related to the application of superposition theorem with both independent and dependent sources. So in this video we are going to start the next network theorem, which is Thevenin theorem. So first we'll discuss the basic concept or basic statement of Thevenin's theorem, and then like we did in superposition theorem we will understand it with the help of questions, problems. Various types of problems will take, various types of circuits will take with both independent and dependent sources. Okay, so why Thevenin theorem is required, or what is the requirement of this Thevenin theorem? So the main objective of any network theorem, be it superposition, Thevenin, Norton, maximum power transfer, reciprocity, whichever network theorem you take, the main objective is basically to simplify a large complicated network, to bring it into a simple form. That is the objective, to make our calculations easy. So that is the objective of superposition theorem, that is the objective of Thevenin theorem, that is the objective of Norton theorem, which we will cover in the next videos. So Thevenin theorem, what it does is that it converts a large circuit, be it any number of voltage sources are there, 3, 4, 5, 6 current sources are there, whatever number of resistors are there, it converts it into a simplified form which consists of a voltage source which is called as the Thevenin equivalent voltage. Okay, we'll come to that. It converts the complicated network into a simple form consisting of a voltage source in series with a resistance. See, such a huge circuit consisting of multiple voltage and current sources, multiple resistors. Now we are only sticking to resistors. In AC analysis we'll discuss the Thevenin theorem related to inductors, capacitors, all that. Now we will just stick to resistors. Okay, it consists of many resistors, voltage and current sources. All of that is converted, reduced into a simple form consisting of a voltage source in series with a resistance. That is the whole objective of Thevenin theorem. So the statement of Thevenin theorem is that any linear, bilateral or two-terminal DC network means only resistors, DC voltage and current sources, containing more than one energy source, be it any number of voltage or current sources, it can be replaced by a simple equivalent circuit consisting of a single voltage source in series with a resistance. That voltage source is called as the Thevenin voltage and that resistance is called as the Thevenin resistance. So linear and bilateral elements, we also discussed it in superposition theorem. So linear elements are those which obey Ohm's law, and the bilateral elements, they allow or permit the flow of currents in both directions. Okay, so that is linear and bilateral. So let us say we have a circuit like this. Here we have a network, circuit network. It consists of an independent voltage source, two resistors R1 and R2 connected in this way, a independent current source. This is the circuit. Suppose we have to find the Thevenin equivalent circuit of this network. What is the Thevenin equivalent circuit of this network? So for that we have to pick two terminals, 2 points across which we want to determine the Thevenin equivalent. Suppose we pick these 2 points across the independent current source. Suppose we pick these 2 points. Across these 2 points, 1 and 2, we have to determine the Thevenin equivalent circuit. So the Thevenin equivalent of this circuit would look something like this. All this independent voltage source V, R1, R2, I, it is same as the Thevenin voltage in series with the Thevenin resistance. So VTH and RTH are to be separately determined, and there are rules, certain rules and regulations associated with it. So the Thevenin voltage is the open circuit voltage, or the voltage across these two terminals 1 and 2, with all the independent and dependent sources, if they are there, they are kept intact. Okay, considering all the independent and dependent sources, the voltage across these two terminals across which the Thevenin circuit has to be determined, that voltage is the Thevenin voltage. So we have to determine it using any circuit analysis technique, be it mesh analysis, be it nodal analysis, be it source transformation, be it star delta transformation, current division rule, voltage division rule, KVL, KCL, whatever is needed we will do. We will apply it and find this voltage. That is our objective, to find the open circuit voltage across the 2 points across which the Thevenin circuit have to be determined. Okay, we calculated VTH. First step is accomplished. We have calculated VTH. Next thing is to determine the Thevenin resistance. To determine the Thevenin resistance, what is done is that the independent sources, that will be the independent voltage or current source, they have to be deactivated. They have to be deactivated. So how deactivation of independent source is done? Voltage sources are short circuited, current sources are open circuited. Okay, independent sources are deactivated, voltage sources short circuited, current sources open circuited. So with this being done, the equivalent resistance is calculated across the same two terminals, series or parallel, equivalent, whatever, in which way the resistors are connected, we have to determine the equivalent resistance. So that equivalent resistance with all the independent sources deactivated is the Thevenin resistance. For dependent sources present in the circuit, the analysis is a little bit different. We will take that up when we will discuss that. Okay, the dependent sources, Thevenin theorem with dependent sources. So that will be a separate series of videos. This is just for independent sources. So this is the Thevenin resistance. So we determined both VTH and RTH, 2 steps. Then we form this circuit, the equivalent circuit, VTH and in series with VTH, RTH. This is the Thevenin equivalent of this circuit network across the two terminals 1 and 2 of this independent current source. So we can determine the Thevenin equivalent across any two terminals. Suppose you want to determine the Thevenin equivalent across these 2 points of the independent voltage source. So same thing, first we have to determine VTH, then we have to determine RTH, deactivating the independent dependent source. Suppose we want to determine the Thevenin equivalent of this circuit network across R2. For that we have to remove R2, open circuit it, find the VTH, the voltage across these 2 points, then RTH. So same, we can determine the Thevenin equivalent in a circuit network across any 2 points, across R1, these 2 points across R1. For that we have to open circuit it first, VTH, then RTH. So like that, it is just a simple circuit. It is just a simple circuit here. No matter how complicated it is, how many number of resistors are there, how many number of voltage or current sources are there, we can determine the Thevenin equivalent circuit. The calculations will be a little bit more, lengthy. It can be lengthy when the number of voltage sources, current sources, resistors are increased. The calculations will be a little bit tricky, but we can determine it. So mostly the questions, the that come for solving in exams, it involves very simple circuitry, conceptual but simple. So this is the whole point of Thevenin's theorem. So we can convert any linear two-terminal network across any 2 points to determine the Thevenin equivalent. We can convert any linear two-terminal network into this form, VTH in series with RTH. So this is the equivalent Thevenin representation. VTH in series with RTH is the equivalent representation of the two-terminal linear network. Okay, so let us understand. We will understand when we'll solve the problems. You will understand it in a better way. Okay. So we just discussed about the general statement of Thevenin's theorem, and we discussed some related things about Thevenin voltage and the Thevenin resistance, the equivalent resistance. So now we will just discuss how this Thevenin theorem actually works, what exactly it does. Okay, so according to the Thevenin theorem, any linear two-terminal network can be replaced by a voltage source, equivalent voltage source in series with an equivalent resistance. The voltage is called as Thevenin voltage and the resistance is called as Thevenin resistance. Let us say we have a circuit, okay, and we have some resistors, we have voltage source, current source, like this. Okay, so this is a circuit, R1, R2, R3 and R4. We have a circuit like this. Now let us say we want to determine the Thevenin equivalent across these 2 points, point 1, point 2. So what we have to do and what that essentially means, it means all of this, okay, all of this portion within the dotted boundaries, we will replace it, all of the voltage source R1, R2, R3, the current source, we will replace it with a voltage source in series with a resistance. These 2 points across 1 and 2, all of this voltage, resistor 1, resistor 2, resistor 3 and this independent current source, we have to replace it with this VTH, the Thevenin voltage, and the Thevenin resistance. This is the whole point of Thevenin's theorem. What it does is it basically simplifies the whole circuit. Now we can reconnect this resistance R4 and we can do whatever analysis with it. So this VTH and RTH, voltage source in series with this resistance, is equivalent to this whole network, voltage, resistor R1, R2, R3 and this. All the network elements connected in the way they are within this dotted region, they are the same as VTH and RTH. This is the whole point of Thevenin's theorem. Now we can determine the current flowing through R4, or we can determine the voltage drop across R4, whatever we want to do. Okay, it simplifies the circuit. So now we will discuss how to apply Thevenin's theorem with the help of suitable examples. Okay, so this is the first question that we are going to discuss on the application of Thevenin's theorem. So it is a very simple circuit because it consists of only one voltage source, an independent voltage source, and it has 4 resistors, and we have to determine this current I flowing through the 7 ohm resistor. Okay, so let us do that. So we will do it with the help of Thevenin's theorem. We have already discussed about superposition theorem application. Here we will discuss about how to do it using Thevenin's theorem. So Thevenin's theorem application requires 2 important things to be determined. First is the Thevenin's voltage, second is the Thevenin resistance. Only then we can form this circuit, VTH, RTH. So these 2 things we have to determine. Okay, so here it has been asked to find the current flowing through the 7 ohm resistor. So what we will do, let us redraw the circuit. Okay, this is 7 ohm, this is 13 ohm, this is 30 ohm, this is 60 ohm, this is 240 volt. So it has been asked to find this current. So what we will do, we will first remove this resistor. First step, just remove the resistor. Open the terminals, name them 1 and 2, A or B, whatever, X, Y, whatever you want to name. Now we have to determine the equivalent Thevenin circuit of this network, excluding the 7 ohm resistor. All the remaining network elements, circuit elements that are present, 13 ohm, 30 ohm, 60 ohm, 240 volt, we have to determine the Thevenin equivalent circuit of it. So first step, Thevenin voltage. Thevenin voltage is this voltage. Okay, this voltage is the Thevenin voltage across the open terminals 1 and 2. We have to determine this, the open circuit voltage across these 2 terminals 1 and 2, that is the Thevenin voltage. We can determine it in any way that we want. We can use mesh analysis, we can use nodal analysis, we can use voltage division rule, current division rule, apply any circuit law, technique, whatever you want to do, but determine this Thevenin voltage. So here we can apply basic voltage division rule. See, this current here is 0 ampere because it is open circuited. So it means whatever current flows through this term, this 60 ohm resistor, same current will flow through 30 ohm. It means 60 ohm and 30 ohm, they are in series connection. Okay, so we will determine the voltage across this 30 ohm resistor, and that will be our Thevenin voltage. So voltage division rule, we have already discussed it, so we'll apply. So VTH is equal to the voltage drop across 30 ohm resistor, 240 into 30 by the sum 60 plus 30. So it is 240 into 30 by 90. This is 3, this is 80. So VTH is equal to 80 volt. We have calculated VTH. Let us write it down here. VTH is equal to 80 volt. So get the point clear about Thevenin voltage. When we open circuit a particular terminal, the voltage across those two terminals is the Thevenin voltage. Here we open circuited the 7 ohm resistor. Suppose we would have open circuited the 30 ohm resistor. Okay, I am just rubbing it here and I am reconnecting this whole thing, that is 7 ohm, and I have open circuited the 30 ohm resistor. So let us name the points 1 and 2. In this case, we have to determine the Thevenin equivalent across these two terminals. Okay, so here this circuit 240 volt, 60 ohm, 13 ohm and 7 ohm will have to be replaced by the equivalent Thevenin circuit. In this case, we have to determine the Thevenin equivalent across the 30 ohm resistor terminals, open circuited terminals. Similarly, you can do so across the 13 ohm, you can do so across the 60 ohm, you can do across any two terminals. Any two terminals across any 2 points, you can determine the Thevenin equivalent circuit. But here, as it was asked to find the current through the 7 ohm resistor, that's why we are finding the Thevenin equivalent across this 7 ohm circuitry. So we are replacing all of this network, the voltage source 60 ohm, 30 ohm, 13 ohm, with its equivalent Thevenin circuit for simplicity of calculations. Okay, so you can find the Thevenin equivalent circuit across any 2 points in a network. Okay, just by open circuiting it. First step, we have to calculate the Thevenin voltage by any means you want: voltage division, current division, nodal analysis, mesh analysis, KVL, KCL, apply anything, star delta transformation, do whatever you want, but find VTH and then RTH. So we have found VTH in this case. Now let us find the RTH. Okay, so now in the second step, we have to determine the Thevenin resistance, the Thevenin equivalent resistance. So here our target is the 7 ohm resistor, the 2 points. So across the 7 ohm resistor, the 2 points connecting the 7 ohm resistor, we have to determine the Thevenin equivalent resistance of the excluding network, the remaining network, that is 13 ohm, 30 ohm, 60 ohm and 240 volt. So for doing that, what we have to do, again we remove the 7 ohm resistor, same as we did for VTH calculation. 1, 2. Across this 2 points, we have to determine RTH. And there is one extra step here. You have to deactivate the voltage sources and current sources. Voltage sources have to be replaced by short circuit. Current sources have to be replaced by open circuit. Same as we did in superposition theorem, considering one source at a time. We deactivated the other sources. If we considered one current source or a particular current source, we have to deactivate the remaining voltage sources and current sources. If we considered a voltage source, we have to deactivate the remaining voltage sources and current sources. Voltage sources were short circuited, current sources were open circuited. The same principle. So here we have to determine the Thevenin resistance. So here clearly you can see that across these 2 points 1 and 2, 30 and 60, they are in parallel connection, and the equivalent of 60 and 30 is in series with 13. Okay, so this will be 60 parallel 30, these two, plus 13, that is RTH, or it is 60 into 30 by 90, 60 plus 30 plus 13, this is 3, this is 20, this is 33 ohms. RTH is 33 ohms. VTH was 80 volts. VTH was 80 volts. So the Thevenin equivalent circuit can be drawn as like this. 80 volts VTH, RTH is 33 ohm across points 1 and 2. But in the question our objective was to find the current through the 7 ohm resistor. So we found out the equivalent Thevenin circuit for this network, excluding this. So all of this 13 ohm, 30 ohm, 60 ohm, 240 volt connected in the way they are is same as this 80 volt in the series with 33 ohm. So now to determine the current through the 7 ohm resistor, we will reconnect it back. 7 ohm, you have to find the current. So I is equal to total voltage by total resistance, which is 4080 volt by 40 ohm, which is equal to 2 ampere. So this current flowing through the 7 ohm resistor is equal to 2 ampere. As per Thevenin's, we did it using Thevenin's theorem. Okay, this is 2 ampere. Okay, so this is the application of Thevenin's theorem to determine any circuit parameter, voltage, current, whatever. So we could have solved it using superposition theorem. We will solve using Norton's theorem in the future when I will post videos related to that. So different kind of techniques can be applied. We could have used mesh analysis, we could have used nodal analysis, we could have done whatever we want. But here our objective was to find it using Thevenin's theorem. So we did it using the steps that we used. Okay, so this is the basic example related to application of superposition theorem. It was very simple, only one voltage source was there. So we'll discuss some more questions. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering. Have a great day. Thank you very much.